So number 68 in chapter 17, we have a man who wishes to vacuum his car with a canister vacuum cleaner marked with 535 watts power at 120 volts. The car is parked really far from the building, so he needs to use an extension cord, right? And that's length of 15 meters. And we have to assume the cleaner itself has constant resistance, which we'll call R naught in this case. So then we're also told that the resistance of each of the two conductors in the cable is 0.9 ohms. And we want to know what is the actual power delivered to the cleaner. Because he's added this extension cable into the mix, it's not going to be the 535 watts. So we want to know the actual power delivered to the vacuum. So what this is going to be is power is equal to, what do we have? Let's double check this. We had IR of the vacuum, the resistance of the vacuum, the total current, right? And I think it might be squared. That's what I'm looking for here. So if I check the summary, it is squared. So there we go. So power is equal to current squared times the resistance of the vacuum. And this is going to be the current flowing through the vacuum itself and also the cable, right? So what we're going to need to figure out, because if we recall that current is defined in terms of, is defined in terms of delta V squared over R. Right. It's also, yep, that's actually what we want. We want to use Ohm's law. So, okay, so moving on. So what we have here then, because this is current of the vacuum and the cord, this is going to be total resistance of both of those things. The change in the potential is going to stay the same across the system. So we need to figure out what is the total resistance. So starting with what we're given in the beginning, we're told that we have a constant constant resistance, which is using Ohm's law, have 120 volts squared. Sorry, this is not Ohm's law, this is, well, it is essentially, but this is in terms of power, right? So we have actually the V squared over P. That's what we have here. Okay, and the reason I squared this was a mistake because I was looking here. This is Ohm's law here. This is Ohm's law redefined in terms of power. So we have resistance is equal to change in the potential over power, right? And so using this, we can actually just find an explicit value for the resistance of the vacuum cleaner, right? So it is R naught is equal to 26.92 ohms. Okay, so again, I did make a mistake here. Ohm's law is V equals I times R. So I just rearranged. And this is in terms of power. Delta V squared over P. Like that. Okay. So next we're going to have to add up. Remember, we wanted to sum up the total resistance because we need the total current. So then we want the current of the vacuum, and recall that that was 0.9 ohms for each of two conductors inside the cable. So total, let's see, so we have a total resistance for the whole system is equal to R naught, which we have up here, plus 2 times RC, because we have two conductors in the cable. Okay? So then, what does that give us? It gives us 26.92 ohms plus 2, we'll just say it's 1.8, right? 1.8 ohms. That's our total resistance. Okay, good. Next then, we want to plug this into our formula. So what did we have? We wanted total power delivered to the vacuum at the end of all of this. So P vacuum is equal to I squared times resistance of the vacuum, where I squared is the total current squared. So that's going to give us delta V squared over RT squared times R of the vacuum. So that's 120 volts squared times R of the vacuum, which was, what was it, 26.92 ohms, all over, what was it? It was 26.92 ohms plus 1.8 ohms all squared. And so this is going to give us a value of 470.03 watts. So that's the total power delivered to the vacuum. So it's it's way less than what we actually need because we added this long cable in the mix. Okay,